Hi, my name is David and I will present the Cascade Control. Whenever we have two or more processes connected in series or cascade, it is very convenient to use Cascade Control. Cascade Control consists in making one closed loop control for each process individually instead of using just one control for the whole process. Let's say we have one process G of S which consists in one motor the process 1 uh, or G1 and a set of lender blades process 2 or G2. Now, suppose that in order to be efficient in the blender has to get to a given velocity as fast as possible and maintain it independently of the hardness of the product, the disturbances. In this case, cascade control may be interesting because with that technique we can protect the intermediate processes from disturbances originated in their operation, like in this case, noise from the power supply. So how does it work? Well, basically, we substitute the classical or traditional closed loop control like this. We have G1 and G2, the processes to be controlled, and C of S, the control. We substitute that to a double or triple cascade closed loop control like this. First, we will design C1 of S control for the first process G1 of S, and we will design that and implement that in closed loop, and we can now substitute or see this block like H1 of S like this. With that, we will we design the process C2 of S like we will do in the traditional case. Uh, before implementing any control, we have to know that the inner loop needs to be quite faster than the outer loop. So we have to design the C1 control to be quite faster, so the outer loop uh, doesn't need to be so slow. For example, uh, let be the next block H1 of S, closed loop control for G1 and the control C1 of S. We can see that there is a sum block added at the end of the block, and the block is there for adding disturbances in the simulation. Then we have the second process G2 of S following H1 of S, and we need to design a PI control for such a process. And for that, we will execute a unitary experiment for the whole process in series, and we obtain a first order like graph. So that means that we can fit the process to a first order with delay model, GF of S, like this. So we will obtain a system, and solving the system, we obtain the parameters of the fitting, and we can tune the control C2 using the analytical PI tune rule for first order models with delay, like this. And we say that the tau I is tau or 1.521, tau C is 1.5, and Kc is 0.605. Before testing the cascade control, let's implement a traditional PI control using the same rule and we do the step experiment. We fit the model to a first order model with delay. We obtain the control, the PI control for such a process, and with that we implement all the processes or the controllers in Simulink and we compare it. The results of the compare is or the experiment are here. With that, we have in blue uh, the cascade control and in red the traditional control. And the upper graph is for the output of the G2 process, and the second graph is for the first process G1. In both cases, in both graphs, we can see that the cascade control is faster, has less oscillation, has less overshoot, um, uh, uh, has less undershoot um, than the traditional control. Then we add a disturbance to the first process G1, and we can see that again there is faster, there is almost no overshoot, there is almost no oscillations. In the second process G2 is less affected by the disturbances in inner loops in the case of the cascade control. And finally, in disturbances of the disturbances in the second process, we have again less oscillations, less overshoot, almost no undershoot, is faster. So in this case, the cascade control is better in a sense than the traditional uh, control. Thank you.